All right, line U2, learning task 1, we're going to describe cathodic maintenance. And cathodic maintenance is really going to vary upon the type of system that we are going to go and have. If we've got galvanic cathodic protection, we are going to go and have just, chunks of sacrificial metal, zincs, aluminums, and stuff like that that are going to be bolted onto our steel structure. You see that over here, that the steel itself has got these fastened down onto that, and then this becomes the sacrificial anode, right? Those electrons flow through here, they get broken down in the weak acid, they flow through here, and they get deposited back onto the surface of the structure that we're trying to go and protect. This picture over here is from a boat because that's, one of the most common places that we have these sacrificial anodes on there. But it's not, that far off from what we have on structures or on pipelines. If it is something like this, it's not going to be something we are going to deal with, though. If it's galvanic cathodic protection, that's going to be taken care of by the millwrights and other maintenance personnel that are going to be, dealing with more of the mechanical end. For us, we have the ICCPs that we go and maintain, and ICCPs are going to be in the post-current cathodic type of protection. Now, my ICCPs do also have a set of anodes. Those are usually going to be those graphite rods that are going to be buried inside of the coke mixture, right? And they do go and degrade over time. So we will still have to go and maintain our anode array. A couple of things that we're going to be looking for on cathodic protection systems is going to be, first of all, the anodes. You got to make sure that they are going to be buried well into their bedding mass. That's the coked mixture. We also need to go and make sure that they're actually, sizable enough. They are going to be usually cylindrical. And what happens to a cylinder is if you lose like a, 5 millimeters around the whole circumference of a cylinder, if that gets eaten away, you have a greatly reduced amount of surface area because it's shrinking in on all sides. So you do just have to, maintain and replace at times. The other thing that we need to go and make sure of is that our connections stay tight. That we don't have any high resistance connections, whether that's going to be going onto the pipeline or the vessel that we're trying to go and protect, or whether that's going to be, the connections to the anode or anything like that. As soon as you end up with loose connections, you end up with a bit of high resistance. And that high resistance is going to block that tiny amount of current. These are not huge current types of systems, right? So we need to go and have a low resistance so that we can be passing all of those electrons through the protected device itself, the pipeline, the bridge, whatever it is that we are trying to go and protect. So check for any sort of loose connections. Those are going to give you the high ones. And then you have to be careful as well with where you utilize these things and how they're brought in. Oftentimes, we will use them for protection on oil and gas systems. And there's a bit of a danger that comes along with that because now we're dealing with current that is being placed over top of something that is carrying something flammable, right? It can be done safely, and as long as there's no extraordinary types of faults on the system, it should not have any issue. But you do still need to be aware of that yourself when you're working around these things, that there's going to be potential difference, voltages that we are going to go and see, as well as there's going to go and be current flow that needs to happen through them. So if you go and pull apart, or if a millwright who's unaware because you haven't put up proper warning signs pulls apart a pipe, to take a look, there's going to be an arc that's going to go and happen across the gap itself. They should be tested in order to go and, check for the fact that we've got the correct low value of resistance, that we're still flowing the proper amount of current through there. And then all of your testing is always going to need to be logged inside of here. If you log your testing, what you're looking for is you're looking for differences. You shouldn't just be logging, you should always be scanning what was the previous test results. And if all of a sudden your test results are showing massively different, characteristics on the system, that usually is indicative of some sort of a failure or a fault or something that is starting to go and come apart. Let's take a quick look inside the Canadian Electrical Code because we deal with the cathodic protections inside there. They have their own section. All right, Section 80 of your Canadian Electrical Code is going to deal with cathodic protection. And note that the top of the section states that this section only applies to the installation of impressed current cathodic protection systems. It's got nothing to do with, those bolted-on anodes, the sacrificial ones that we would have. And it's going to go and supplement or amend the general requirements of the code. In other words, any of these, sections, the latter parts of the code, they're always going to have this, that supplements or amends. You follow regular code first, and then you do the additional requirements, that based upon the system that you're working on. So DC wiring, that we are going to go and have, the conductors are always going to be DC for cathodic. They have to be wiring below ground shall be permitted to be buried at a depth of not less than 450 millimeters. It's shallower than what we normally have for underground installations because we're just looking at, cathodic protection. It's not like we need to isolate from stuff because usually these are going to be attached to something that's already going to be fully touchable, walk aroundable, etc. on the surface. So what's the point of really, burying it deep? We're not preventing much in the way of shock hazard. We do have to go and make sure it conforms in hazardous areas to sections 18 and 20, so the types of wiring that we're going to need to have. And then if I've got a class 1 area, now classes are going to be areas that are classified out of my section 18, then I'm going to have to go and follow, some additional rules over here. Once again, hazardous location rules based upon, the presence of flammable gases. The conductors cannot be smaller than a number 12 AWG. It's not because we got a lot of current that needs to flow along them. It's because we need the conductors to be robust enough that they are going to go and survive. And then if I'm looking for reference electrodes, that's going to be for voltage or for other instrumentation, amperage, I am allowed to use smaller than number 12. That's going to be for my sensors that are just, continuously on board on the system, making sure that it is going to be, still active. Taps and splices are permitted to be made in the DC wiring below ground, provided that they're made by welding and they are sealed against moisture. Usually taps and splices for most of our wiring has to go and happen in a box that has to be accessible. But in this case, because we're usually dealing with, once again, pipelines that are going to be partially buried or, maybe fully buried, we're allowed to splice these things underground. And then if they're exposed to the weather, splices and taps have to be in accordance with subrule 1. Once again, made by welding and sealed against moisture. Connections to the piping, so where our conductors go to the piping, have to be made by means of thermit welding. That's going to be my my chemical type of welding where it's powdered aluminum and copper that are going to be ignited together, that they melt down to form a weld in there. Or it has to be a clamp that is the same material as the piping. This is very specific. You can't just place any old clamp or lug onto stuff because the whole thing is, we're trying to prevent galvanic reactions, right? That transfer of current that's going to happen, corrosion. So if you would go and have, a copper conductor and then you stick an aluminum clamp onto your pipeline or whatever it is that you're trying to deal with, you inherently have galvanic reaction. If you've got a steel pipeline, you need a steel clamp. Otherwise, if you don't know what it, or if you can't get, the same type as your pipeline, maybe it's stainless steel, you can't find stainless steel clamps, they are available. But, maybe you can't find them, you'd have to find something that's going to be anodic to the piping. And to do that, you're going to have to go into the chemistry of the piping. So you need to know exactly what type of steel you're dealing with. Is it, mild rolled? Is it Corten? The actual chemical construction of that. You'd find that out from the manufacturer, and then you'd have to find a metal that is going to be anodic compared to it. The rest of those are pretty straightforward. The branch circuit supplying the rectifier has to be in accordance with the requirements of section 12, so wired as we normally would. That's the circuit that goes to the power supply for these. And it has to be for the cathodic protection rectifier alone. You're not allowed to share it with anything else. And then you need to have separate disconnecting means. Shall be installed at a point readily accessible to users and within sight of and within 15 meters of a rectifier unit. So there has to be a disconnect within 15 meters. Can be closer. It has to be just within that section that we're going to have so that if there's problems, people can go and shut it down. And then notwithstanding subrule 1, your disconnecting means is allowed to be part of the rectifier unit. So it can have a breaker handle on it, etc., as long as, it follows the rest of these requirements underneath here. It does need to be labeled. And this is a general code requirement back in section 2, but it's reiterated over here in a conspicuous, legible, and permanent manner, identifying it as a disconnecting means for the cathodic protection system. Once again, because it's going to be live piping and things like that, we need to make sure that maintenance personnel could shut her down if and when necessary. Okay, 80.012, operating voltages that we will have for these. When a cathodic protection system has a maximum available voltage of more than 50 volts, note that it states over here that we can go higher than 50 volts. We're not limited to 50 volts. But, generally speaking, we're going to keep it underneath 50 volts. Once we go above 50 volts, we've got specialty requirements, and that's going to be these. The voltage potential, our difference between any exposed points on the protected system, so like piping that's above ground, or any point in the vicinity of the anode, and any point 1 meter away on the earth shall not exceed 10 volts. So there is going to be voltage drop that happens along the system. What they're saying is that if I'm standing on the earth, the dirt, and I'm touching the pipe itself, I better not have any voltage that I can see and sense that's more than 10 volts. Yes, we might be feeding the system with 50 volts, but that 50 volts, or maybe 70 volts or something higher than 50 volts is going to go and be spread out along the length of the pipe that you're going to have. Okay. Warning signs. Warning signs are going to be huge because we don't want to have any sort of arc flash, small amounts of current and voltage, yes, but enough that it can still go and strike an arc, and that arc would be highly, highly damaging to, a oil and gas installation, causes fires and explosions. So tanks, piping, or structures protected by cathodic protection system. Remember, this is only to do with the imposed current one, so not with the galvanic one, but anything that's current, shall bear a marking either on the structure or on a tag attached to the conductor close to the connection to the structure, warning that the connection is not to be disconnected unless the power source is turned off. So you need to have identification on the structure itself. You need to have another sign in a conspicuous location, that means like readily seeable, adjacent to the disconnected means for any electrical apparatus connected to cathodically protected structures, advising before the equipment or piping is replaced or modified that the cathodic protection must be turned off, and temporary cathodic protection bypass conductors sized for the maximum available current must be installed. In other words, if there's a chunk of pipe being taken out for resurfacing or something like that, you'd have to go and stick a conductor that would make the connection. We're taking out a 10-foot chunk of pipe. There'd have to be a connection that gets made branching that so that you can once again use that system on the rest of the pipe that needs to be protected. In a non-hazardous location, so notwithstanding this one over here, this is going to be our general one, but if it's a non-hazardous location, which means that we wouldn't be carrying oil or gas or anything like that inside of it, maybe it's salt water that you're carrying through there or something, the required sign shall be permitted to advise the use of a temporary conductor sized for the maximum available current to bypass the location where it's to be replaced or modified as an alternative to turning off the cathodic protection. So if, in general speaking, it should always be turned off. That's what we're seeing in Subrule 2. Subrule 3 says, look, if you're carrying something else. Salt water is something sometimes used for cooling on systems that are going to be, down ocean side. We'll pipe that stuff through, but we do need to cathodically protect it. If, there's the piping gets taken out, it's not going to go and cause any sort of issue. You get a small little arc, but it's not going to light anything up. So in this case, what you're allowed to do is you're allowed to go and stick a bypass conductor around the section you're taking out, and then take the section out while it's still live. There does have to be a drawing showing the location of underground water, the polarity, underground wiring, the polarity, what's positive, and where the anodes are has to be provided inside the rectifier cabinet or in a location near the cabinet so that it's able to be traced around, etc. And when the immersed surfaces of a storage or process container are cathodically protected, a note shall be placed in a conspicuous location adjacent to the entranceway, advising that the cathodic protection system must be turned off before the container is entered. All right, that is a relatively short section of the code. We see we're down to section 82 down here, which is deleted, so that's all that there is inside of here. But yeah, know that there is a code section that is dealing with these things, and be very aware that if there's cathodic protection, there needs to be a lot of signs and warnings so people understand what it is that they are dealing with.